Nature of mathematical statements. Hello class, today we are going to study about the nature of mathematical statements. We know that mathematics is not just number and a lot of logic is involved. We prove theorems, make propositions, derive and design complex systems based on logic which have a structure to it. We will further say in the lecture that logic is not merely an abstract concept, but are actually rules that one must follow in order to arrive at a meaningful destination. Basketball, football, cricket, or any sport for that matter have a set of rules that the player must always obey while playing the sport. Similarly, mathematics in general and logic in particular is built upon a set of rules, namely axioms and postulates. An axiom or postulate is a statement that is taken to be true to serve as a premise or starting point for further reasoning and arguments. The word comes from the Greek axioma, that which is thought worthy or fit, or that which commends itself as evident. The term has subtle differences in definition when used in the context of different fields of study. As defined in classical philosophy, an axiom is a statement that is so evident or well established that it is accepted without controversy or question. As used in modern logic, an axiom is simply a premise or starting point for reasoning. As used in mathematics, the term axiom is used in two related but distinguishable senses: logical axioms and non-logical axioms. Logical axioms are usually statements that are taken to be true within the system of logic they define. For example, A and B implies A, often shown in symbolic form, while non-logical axioms, for example, A plus B equals B plus A, are actually substantive assertions about the elements of the domain of a specific mathematical theory, such as arithmetic. When used in the latter sense, axiom, postulate and assumption may be used interchangeably. In general, a non-logical axiom is not a self-evident truth, but rather a formal logical expression used in deduction to build a mathematical theory. As modern mathematics admits multiple, equally true systems of logic, precisely the same thing must be said for logical axioms. They both define and are specific to the particular system of logic that is being invoked. To axiomatize a system of knowledge is to show that its claims can be derived from a small, well understood set of sentences. There are typically multiple ways to axiomatize a given mathematical domain. In both senses, an axiom is any mathematical statement that serves as a starting point from which other statements are logically derived. Within the system, they define axioms, unless redundant, cannot be derived by principles of deduction, nor are they demonstrable by mathematical proofs, simply because they are starting points. There is nothing else from which they logically follow, otherwise they would be classified as theorems. However, an axiom in one system may be a theorem in another, and vice versa. Now we shall see in detail about the nature of mathematical statements, axioms and postulates. Euclid's Elements is a mathematical and geometric treatise consisting of 13 books attributed to the ancient Greek mathematician Euclid in Alexandria, Ptolemaic Egypt, circa 300 BC. It is a collection of definitions, postulates, propositions, theorems and constructions, and mathematical proofs of the propositions. The books cover Euclidean geometry and the ancient Greek version of elementary number theory. The work also includes an algebraic system that has become known as geometric algebra, which is powerful enough to solve many algebraic problems including the problem of finding the square root of a number. Elements is the second oldest extant Greek mathematical treatise after Autolycus on the moving sphere, and it is the oldest extant axiomatic deductive treatment of mathematics. It has proven instrumental in the development of logic and modern science. Euclid's Elements has been referred to as the most successful and influential textbook ever written. Being first set in type in Venice in 1482, it is one of the very earliest mathematical works to be printed after the invention of the printing press, and was estimated by Carl Benjamin Boyer to be second only to the Bible in the number of editions published, with the number reaching well over 1,000. For centuries, when the quadrivium was included in the curriculum of university students, knowledge of at least part of Euclid's Elements was required of all students. Not until the 20th century, by which time its content was universally taught through other school textbooks, did it cease to be considered something all educated people had read. Euclid, the legendary Greek mathematician, also known as the father of geometry, is credited with the creation of axioms and postulates. Euclid was active in Alexandria during the reign of Ptolemy I, 323 to 283 BCE. His book Elements is one of the most influential works in the history of mathematics, serving as the main textbook for teaching mathematics, especially geometry, from the time of its publication until the late 19th or 20th century. Euclid's biggest accomplishment is to present mathematical ideas of earlier mathematicians in a single, logically coherent framework, making it easy to use and easy to reference, including a system of rigorous mathematical proofs that remain the basis of mathematics 23 centuries later. In modern mathematics, the first principles of any formal deductive system are axioms. Informally, they can be compared to the rules of a game. Although the words axioms and postulates are used interchangeably in mathematics, Euclid intended that they should be used differently. Axioms or common notions are truths which cannot be proved but are universally accepted to be true. Postulates are statements which are true but are also assumptions. Some authors who study Euclid's work also say that axioms are general truths that can be used in any mathematical environment, but postulates are only for geometry. It is important to note that Euclid's Elements primarily deals with geometry. The geometrical system described in the Elements was long known simply as geometry and was considered to be the only geometry possible. Today, however, the system is often referred to as Euclidean geometry to differentiate it from the non-Euclidean geometry discovered in the 19th century. The method of logic is to know something or to prove it through reasoning. In the Victorian era, late 19th century, the famous author Sir Arthur Conan Doyle created an unforgettable fictional character who resides at 221B Baker Street, London. We all know him to be the famous Sherlock Holmes, who is the master of logic and reasoning. It is interesting to note that the character of Sherlock Holmes often harps on the science of deduction and uses it with mathematical precision to detect crime. The word deduce comes from the Latin deducere, where the word de means away from and ducere means to lead. Hence, when we deduce or prove something, we are led from what we know to what we can prove. Sherlock Holmes used a deductive system to solve a crime by first examining and collecting all the facts and data, and later deducing the perpetrator of crime by removing all the impossible elements in the system, thereby arriving at the truth. Likewise, in rigorous mathematics, we start with axioms and postulates, slowly deducing and finally proving a statement. The statements we prove are called theorems, but it is not possible to prove every statement. If we had to, there would be no end. Rather, to prove or explain anything is to do so in terms of something we must acknowledge and accept. They are called axioms and postulates. Logic, which is the science of reasoning, is not founded on reasoning. It is founded on irreducible understanding, on what we call first principles. They provide the basis for proving. The first three principles of Euclid's geometry are the following. Number 1, definition. Number 2, postulates. Number 3, axioms or common notions. Now let's see about definitions. The Greek mathematicians who lived at the time of Euclid thought of geometry as a means to represent the real world. They thought of geometry as an abstract model of the world they lived in. The notions of point, line, surface or plane were derived from what was seen around them. The following are some of the definitions given by Euclid in a bid to understand solid shapes, surfaces and points on a surface. These form the backbone for the study of geometry. A definition clarifies the idea of what is being defined and gives it a name. A definition is reversible. That means that when the conditions of the definition are satisfied, then we may use that word, and conversely, if we use that word, that implies those conditions have been satisfied. A definition is equivalent to an if and only if sentence. For example, number 1, an angle is the inclination of one another of two straight lines that meet. Number 2, the point at which two lines meet is called the vertex of the angle. Number 3, if a straight line that stands on another straight line makes the adjacent angles equal, then each of those angles is called a right angle, and the straight line that stands on the other is called a perpendicular to it. Number 4, an acute angle is less than a right angle. An obtuse angle is greater than a right angle. Number 5, angles are complementary or complements of one another if together they equal a right angle. Angles are supplementary or supplements of one another if together they equal a straight line. Number 6, rectilinear figures are figures bounded by straight lines. A triangle is bounded by 3 straight lines, a quadrilateral by 4, and a polygon by more than 4 straight lines. Number 7, a square is a quadrilateral in which all the sides are equal and all the angles are right angles. Number 8, a regular polygon has equal sides and equal angles. Number 9, an equilateral triangle has 3 equal sides, an isosceles triangle has 2 equal sides, a scalene triangle has 3 unequal sides. Number 10, the vertex angle of a triangle is the angle opposite the base. Number 11, the height of a triangle is the straight line drawn from the vertex perpendicular to the base. Number 12, a right triangle is a triangle that has a right angle. Number 13, figures are congruent when, if one of them were placed on the other, they would exactly coincide. Congruent figures are thus equal to one another in all respects. Number 14, parallel lines are straight lines that are in the same plane and do not meet no matter how far extended in either direction. Number 15, a parallelogram is a quadrilateral whose opposite sides are parallel. Number 16, a circle is a plane figure bounded by one line called the circumference, such that all straight lines drawn from a certain point within the figure to the circumference are equal to one another. Number 17, the point is called the center of the circle. A diameter of a circle is a straight line through the center and terminating in both directions on the circumference. A straight line from the center to the circumference is called a radius, the plural being radii. Next, we shall see about axioms or common notions. Things equal to the same thing are equal to one another. Example, if A equals B and B equals C, then A equals C. If equals are joined to equals, the wholes will be equal. Example, if A equals B, then A plus C equals B plus C. If equals are taken from equals, what remains will be equal. Example, if A equals B, then A minus C equals B minus C. Things that coincide with one another are equal to one another. The whole is greater than the part. Example, A greater than A over 2. Equal magnitudes have equal parts, equal halves, equal thirds, and so on. If A equals B, then A over 2 equals B over 2, A over 3 equals B over 3, A over 4 equals B over 4, etc. We shall see about postulates. A postulate, also sometimes called an axiom, is a statement that is agreed by everyone to be correct. This is useful for creating proofs in mathematics and science, and postulates are often the basic truth of a much larger theory or law. Postulates themselves cannot be proved, but since they are usually obviously correct, this is not a problem. Here is a good example of a postulate given by Euclid in his studies about geometry. 2 points determine a line. Using this postulate and 4 others like it, Euclid brought a new understanding of geometry to the world, and many people think that they are some of the most influential works in geometry even now. Sometimes postulates are not obviously correct but are required for their consequences. The easiest case must be with Albert Einstein's postulate that the universe is homogeneous. This type of postulate was necessary to make possible some major scientific achievements, but can also be problematic since not self-evident. There are also a few characteristics that all postulates should have. Number 1, they should be obvious and easy to understand and should not have too many words that are difficult to explain. Number 2, there should not be very many of them. Number 3, they should all work together without making any strange results. They should be consistent. Number 4, they should also be true when they are alone, so that they can be used independently. Grant the following. Number 1, to draw a straight line from any point to any point. To extend a straight line for as far as we please in a straight line. To draw a circle whose center is the extremity of any straight line and whose radius is the straight line itself. Number 4, all right angles are equal to one another. Number 5, if a straight line that meets 2 straight lines make the interior angles on the same side less than 2 right angles, then those 2 straight lines, if extended, will meet on the same side. That is, if angles 1 and 2 together are less than 2 right angles, then the straight line AB, CD, if extended far enough, will meet on the same side, which is to say that AB and CD are not parallel. We require that the figures of geometry, the triangles, squares, circles, be more than mental objects. We must be able to draw them to represent them in the physical world. The fact that we can draw a figure is what permits us to say that it exists. For as we have noted in the commentary on the definitions, we may not assume that what we have called a triangle or a circle actually exists. The first 3 postulates narrowly set down what we are permitted to draw. Everything else we must prove. Each of those postulates is therefore a problem, a construction that we are asked to consider solved. Grant the following. The instruments of construction are straight edge and compass. Postulate 1 in Fx asks us to grant that what we draw with a straight edge is a straight line. Postulate 3 asks us to grant that the figure we draw with a compass is a circle, and so we will then have an actual figure that refers to the idea of a circle rather than just the word circle. These are the definitions, axioms and postulates as outlined by Euclid, and they form the framework that aids in the study of geometry and mathematics in general. Together, they form the pillars upon which the modern mathematics was built. Dear students, in this session we have seen about the nature of mathematical statements, the axioms, the postulates and the definitions. I hope that this will help you to understand the world of mathematics better. Thank you.